Once again, this kind of thing gets quite complicated, and particularly because we don't really have the statistical tools, analysis tools that we need to really understand this like very well. But just give you a brief description of how this filling up states works. So when you think about the states that are filled up in this metal, the free electrons that are filling up these energy states, I tend to think about it in terms of this density of states, this G of E, and that's number density as a function of the energy of these free electrons, or any free electron. It turns out that that energy density goes as the square root of the energy. The exact form looks like this. It's actually fairly straightforward, just a bunch of constants and then energy to the square root. Then if you add in what is the probability that any of these states is filled, it turns out that it depends on the temperature of that metal. It depends at least a little bit on it. It doesn't actually change all that much overall as the temperature increases. But the simplest temperature to think about it is T equals 0. It's not really a physical thing. You can't really get to 0 temperature. But it's a useful way to think about it. If we do imagine that we have this free electron gas at 0 temperature, then as long as the energy of a state is less than the Fermi energy, it's going to be filled. That's all that the middle diagram is showing there. It's showing 100% for any energy less than the Fermi energy, the probability that that state would be filled. And then you combine both of those two together to give you a picture of the filled states, and you get something like that, right? Where the states are being filled all the way up to the Fermi energy, and then there's no electrons above that. Like I said, the temperature does actually affect this, but not really very strongly. It's a fairly weak relationship, such that if you go to, say, like 1,000 Kelvin, that shape overall of which energy states are filled in this for this electron gas, it looks very much like C, the picture C here, except where it drops a little bit sooner before the Fermi energy, and there's some amount that kind of dips out outside or above the Fermi energy. So that's meaning that when temperature is not 0, there is some probability that these highest energy electrons are going to be above the Fermi energy. But the vast majority of the electrons are still below that Fermi energy. And what is that Fermi energy for some different elements? Aluminum, copper, gold, iron. These are some examples of the Fermi energy. 11, 12-ish electron volts, anywhere from a few electron volts to dozen-ish electron volts. And the left column there is the electron density as 10 to the 28th per cubic meter. You probably already have an understanding, but like there's a lot of electrons in a cubic meter of aluminum. 10 to the 28th, 10 to the 29th actually, there's 18. And even in like a cubic centimeter, right, that's down by a factor of 10 to the 4, so it's like 10 to the 24th electrons in like a cubic centimeter. Free electrons, right, in a cubic centimeter of aluminum. So the way that we thought about the energy of these free electrons in this electron gas was applying Schrodinger's equation with a three-dimensional square law. Right? So we got this as the energy states for each of them. But if you think back when we did the particle in a box, or the square well, whatever you want to call it, before, the width or the length of that well, that box, was very small. And all the ones we were talking about were like nanometers or smaller, maybe a little bit bigger, but very, very small. Now, we're talking about the free electrons, the energy of free electrons, in a macroscopic piece of metal. We're treating that whole piece of metal as like the square well. So the width or the length of that is like centimeters, on the order of centimeters. So that means in that allowed energies, or in the energy states here, L is in the denominator. L got a lot bigger, meaning that the smallest energy available is much, much smaller, and also that the difference between energy levels is much, much smaller. So much so that the energy levels for electrons in this free electron gas is essentially continuous. The difference between energy levels is so tiny that it's essentially just a continuum. As an example, if you think about the amount of energy states between 5 and 0.5 electron volts, there's approximately 10 to the 22nd energy states there. So for all practical purposes, the energy spectrum here is continuous. Do at least one example in this chapter here. Okay, so thinking about a cube of metal, it's 2 centimeters on a side. what is the lowest energy level for an electron in this metal, and not just any electron, right? These are the free electrons in that metal. And then what is the spacing between this energy level and the next energy level? So there we go, we still got our energy levels, and N1, N2, and 3 could be 1, 2, 3, 4, 5 each. Take on all these integers. So the lowest energy level then is going to be when N1, N2, and 3 all equal 1. That's the smallest energy we can get out of that. So N1 equals N2 equals N3. This is for part A. And they all equal 1. I guess we'll worry about part A first right now, because we also want to think of what's the next highest energy level, or the next level above that. Well, that's going to be when one of those integers is 2. That's the next level we can get to. This is the lowest. This would be the next one. This is where 1 and 1, or N2, or N3 equals 2, right? And the others are 1. If you look at the energy, it doesn't really matter which one is 2. They all come out to be the same energy overall. Okay, so in A, what then is the energy when all these integers are 1? I squared h bar squared over 2 times the mass of the electron times the length of the cube squared times 1 squared plus 1 squared plus 1 squared. All of our integers are 1. Let's see. Turns out h bar is 1.05 times 10 to the minus 34 joules seconds. That squared. And 1 squared plus 1 squared plus 1 squared is just 3. 3. 2, mass of the electron. And this length, only length for, well, it's only one length for a cube, side length, squared. Plug all those values in, we get 4.48 times 10 to the minus 34th joules. Very small, very small. As electron volts, 2.0 or 2.80 times 10 to the minus 15th electron volts. Okay. So I was saying that the lowest energy level is incredibly tiny, very, very small amount of energy. Right. So then in B, what's the energy difference between this state and the next state up? Well, we go about it a number of different ways, but really what it comes down to is that this factor is changing to be, say, like 2 squared plus 1 squared plus 1 squared. Okay. So instead of being 3, this factor ends up being 6. So the energy, if we let one of those integers increase, turns out to be, let's put that up here, 5.60 times 10 to the minus 15th, 15 electron volts. It's still very tiny, and well, you know, the difference in these is the same as the energy in the first state. And this is on the order of, again, 10 to the minus 34th joules in terms of joules. Very, very tiny energies. And these are the lowest energy states. It's one energy state, but technically, again, there could be 2 electrons there. One could be spin up and one could be spin down. Again, there's something like 10 to the 24th free electrons in this little chunk of metal. And so the highest energy state that's filled up to, the Fermi energy, is on the order of, you know, electron volts. What is a few electron volts to like a dozen electron volts? Turns out that by the time you get up to that high or that large of an energy, these n values are something like 10 to the 7th, or something like 10 million. So the highest energy electron in the free electron gas have a very high energy state, far higher integers than we thought about probably before. To get at why metals end up being good conductors, other materials are good insulators, whether it's these things called semiconductors, we need a bit more in our understanding of these energy levels, and that ends up coming down to what's known as the band theory. Again, complicated, but simply the band theory starts to treat crystals as essentially a bunch of three-dimensional square wells all next to each other. So the picture here is showing like each of the ions, the nuclei in that crystal lattice, are these positive ions, and in between each of them is this roughly infinite square well, particle box. So again, you kind of see why when we looked at the application of Schrödinger's equation, we looked at particle box. It comes around quite a lot. So how do we get to this band theory? Well, you can understand it, I think, fairly well if we go back to our just two hydrogen atoms and think about bringing them together. So we thought about our two hydrogen atoms coming together to form a bond. I mentioned a couple of times that the electrons in each of those hydrogen atoms need to have opposite spin. One had to be spin up, one had to be spin down. That way they could overlap and occupy the same space because they still had different quantum states. However, if you try to bring them together and they didn't have different spin states, just try to force them together, you can still do that, and the potential associated with that looks like the top line in this energy diagram. It's always repulsive. Right? There's no place where it dips down and the slope is going downward there at all. So that's indicating that you're trying to put these two spin-up electron orbitals over each other. They don't want to be there. They're going to keep trying to push each other apart. The bigger picture then is that we brought these two atoms together, and depending on what the electron states were, there ended up being this split in the possible energy states of these two atoms together. If they were going to bond, then one spin up and one spin down, we get that bottom line, which has that potential well, so that they can actually sit there at a stable position. If they're spin up and spin up, then it's higher energy, but it's also always repulsive. Right? So bring two atoms together, you get sort of this split in these possible energies. That was two atoms, and if we think about bringing more atoms together, if we brought three atoms together, then it ends up splitting that single sort of energy into three. Or if you bring four atoms together, it ends up splitting that energy state into four. If you bring n atoms together, when n is a very large number, and you form a solid, very, very many atoms, you end up getting essentially a continuous spectrum of energy, right? Each of the single energy states splits into a large amount of energies, which end up basically being a continuum. This is what we call an energy band now. And if we draw the energy diagram just along this vertical axis, then the result is that each of these electronic states, for say like a free electron in the metal, ends up splitting into all these different states because there's all these different atoms bringing together. And so that 1s state ends up being this sort of band, where electrons in there essentially have a continuous energy spectrum within that band. Same thing happens for all these other electronic states. S2 splits, S3 splits, and it's even larger because there's more space for electrons there. Right? In 1s and 2s, originally they could only hold 2 electrons each, but for n atoms brought together, that's now 2n electrons in each of these bands, whereas the 2p level could hold 6 electrons to begin with, but again, we're bringing n atoms together, splits it into n states, and so there's actually 6n states in this energy band. Remember, n is a very large number. It's like 10 to the 24th. Okay, so now we can finally get a bit of understanding of why it is that some solids are very good conductors and some are not very good conductors, which really comes down to what's going on in the highest energy band that has electrons in it in that material. So if we think about the highest energy band that's filled for that material, that's what we're going to call now the valence band. And this is a slightly different connotation than when we were talking about the valence electron in a single atom. The valence band for a piece of material, for a solid, is the highest filled energy band. Above that, then, is the conduction band. So in a conductor, that conduction band is only partly filled, which means that the electrons in that conduction band have a lot of options for different energy states that they can get to. Right? Because they're within this band, there's essentially a continuous spectrum of energy that they can have. So you can give them a wide range of energies and kind of set them into different states. As opposed to an insulator, the valence band is filled and the conduction band is also filled, or entirely empty. So when you try to give energy to free electrons in an insulator, either you're trying to give energy to the ones that are in the conduction band, and that conduction band is already filled, there's no energy space available for those electrons to gain that energy, so you can't really gain energy there, or that conduction band is completely empty, and you're trying to give energy to electrons in this valence band, but that valence band is totally filled, so if you want to give energy to any of the electrons, it needs to be enough energy to boost it up to the conduction band, which is a much larger energy gap. So this gap in between the valence band and the conduction band means that in insulators, these electrons very much just don't want to absorb any more energy. Right? They're going to remain kind of the same energy they are, sort of stationary. Right. So conductors have this like partially filled conduction band. Insulators have a fully filled or an empty conduction band. And there's that energy gap in between that valence and the conduction band. Semiconductors are somewhat in between, but actually kind of a special type of insulator where that energy gap is actually fairly small. So like I was saying, if you want to give energy to an electron in an insulator, you need to give it a lot of energy in order to get over that energy gap. However, in these semiconductors, things like silicon and germanium, I think, are natural ones, that energy gap is pretty small. So you don't actually have to give it all of that much energy in order to get it into the conduction band, and then it has all this energy space to move around in. That typical energy gap for an insulator, like 5 to 10 electron volts. For a semiconductor, it's only about 1 electron volt. That energy gap for a semiconductor can be small enough where even thermal energy, just like room temperature, energy associated with room temperature, is enough to promote electrons from the valence band to the conduction band. So depending on the semiconductor, it's not that difficult to get it to become a conducting material, or at least somewhat conducting material. So semiconductors, there's natural ones, like I mentioned, silicon, germanium. There's also like hybridized molecules that make semiconductors. I think indium arsenide was one, gallium phosphide is another. And so they're very interesting materials in themselves because they have this sort of property, but you can make them much more useful by augmenting them slightly. They call it doping. So when you talk about doping a semiconductor, you're basically adding some impurities to that solid, to that crystal lattice. The impurities are other atoms that either have like sort of one more or one less electron than the atoms that make up the semiconductor. So on the left there, I'm showing a doping, which is called like a donor sort of doping, where you add like arsenic to the silicon structure, or the silicon crystal, and that arsenic has the one extra electron over the silicon, or that one extra valence electron, free electron over the silicon. And so the net effect is that you kind of get this one extra electron in the crystal that can float around. That's what's known as a N-type, because you're adding a negative charge to the material. Alternatively, you could dope silicon with aluminum, and aluminum has sort of like one less free electron or available electron than silicon. And so the result of adding or doping silicon with aluminum is you end up with this like hole, this like missing electron. That's what's known as a acceptor impurity or acceptor doping, and also referred to as a p-type semiconductor because you're sort of adding a net positive charge in a way by removing negative charge or having less negative charge than naturally would be there. You have more positive charge overall. So by doing this, you can really change the electronic properties of these semiconductors, and they become incredibly useful. Our modern society is basically built on the back of semiconductors. So the N-type semiconductors, I feel like, is maybe a little bit more easy to understand intuitively. Right? You're adding sort of one extra electron for each donor impurity you put in there, for each kind of odd atom that you put in, like the arsenic and the silicon. So those extra electrons, you can pretty easily understand how they're kind of able to add to the electrical property and kind of make the material more conducting in a way. A less intuitive one is the p-type semiconductor, where you're sort of taking away an electron, and what you end up with is what we call this electron hole, or just a hole. It turns out that hole will act exactly like a positive charge, and it can travel through the material just like a positive charge, and so it can also add to the conducting property of that material or make it more conductive. Like one way to look at it is that when you have this electron hole, then an electron that's near that hole will sort of move in order to fill in that hole, right? It's sort of net positive right there, so that negative electron sort of gets attracted to it, moves over, and the electron moved over, but if you look, that positive hole is moving the opposite direction. The little GIF down here is showing it maybe a little bit better, where the red balls are these negative electrons, and they keep moving over to fill the hole, right? But the hole itself is like a positive entity that's moving the opposite direction. And there's a whole bit that the book goes through having to do with the Hall effect and determining the charge of the things that are moving in a material. And it turns out you could do this experiment with a semiconductor, with these doped semiconductors, and it is in fact the positive holes that are moving in these p-type semiconductors. So it's an odd thing, but I don't know, you just kind of get used to the idea, at least if you think about and work with semiconductors, that the absence of an electron is essentially a positive thing, and that positive thing can move around just like any other positively charged particle. So what does that doping do to the energy levels or the energy bands in these materials? Again, it's a difficult concept here. I actually spent quite a bit of time thinking about this myself. The basic picture here is that the N-type semiconductor, when you dope it with these donor impurities, you end up creating a new band, energy band, that is just below the conduction band of that material. And so free electrons in that material can occupy that donor level, and since it's so close to the conduction band, in fact, generally it's something like a few hundredths of an electron volt difference between that donor level and the conduction level, the electrons in that donor level can fairly easily now go into the conduction band and become conducting and do that cool stuff. Close enough even that room temperature energies are enough to kind of bump those donor level electrons up into the conduction band. So that was the donor one. You're adding extra electrons, and those electrons end up occupying this donor level that's close to the conduction band. In the p-type semiconductors, you end up creating this new band as well, except it's much closer to the valence band. It's just above the valence band. And so now the electrons that are in the valence band, really not that much of an energy gap between there and the acceptor level or the acceptor band. So they can fairly easily bump up into that acceptor band, which leaves a hole in the valence band. And now that hole can start acting like this sort of positive charge that can move around. I hope that makes sense. Difficult concepts to think about, but so again, sort of backbone of our modern society. So it's an interesting thing to try to grasp. Right, so why are they so important? Well, because you could make electronic components like diodes with N-type and P-type materials put together. Right? You combine N-type and P-type in just these kind of slabs, these chunks. You create a PN or an NP junction, and we'll go through this, but the result of that is that you basically make like a one-way valve for current to flow. Okay, so what happens when you put these two different doped semiconductors together? Well, on the left, right away initially, you have the N-type, which has the electrons up in this conduction band, and you have in the P-type, you have these holes in the valence band, and they're fairly far apart. But right at that boundary, there's just some diffusion of the electrons from this conduction band so that they can drop over it into the P-type material and start filling some of those holes in the P-type semiconductor. So the result of those starting to diffuse over is that you're making the P-type material more negatively charged overall and taking away the electrons from the N-type. That one ends up becoming more positively charged overall. And so now that we've changed the energies through that diffusion of electrons, changed the overall energy setup of this interface such that now the electrons that are in the conduction band of the N-type are much lower in energy, and they need to sort of overcome this potential hill, like wall, in order to get into the P-type. So right when you put them together, just those natural diffusion of electrons, you end up with this equilibrium position where there's this fairly large hill that you need to overcome in order to start moving charge across this boundary. So if you take that diode, that NP junction, and you connect it to a voltage source, it's just thinking about DC voltage right now. So if you attach the positive end of a voltage source to the P-type side of this diode, then that positive voltage is going to sort of attract the electrons in the diode, and it's going to repel the holes in the diode. So you end up with electrons flowing towards that positive side and holes flowing towards the negative side. And both of these things are saying, one way or another, this is the flow of a conventional current, right? It's positive current flowing from the positive terminal to the negative terminal. That's what we call the forward bias configuration. The reverse bias then is if you connect the negative side of the voltage source to the P-type conductor, semiconductor, then that negative voltage is going to attract the holes, right, up to in the P-type conductor is going to attract those up there. The positive side hooked up to the N-type is going to attract the electrons, and so you kind of pulled the holes a bit in this P-type upward, and you pulled the electrons in the N-type downward, and then no current is going to flow. Because in order for current to flow in that situation, you would need to either pull electrons, negative charge, from the P-type conductor into the N-type, but P-type conductors don't have any extra negative charge, right? They have positive holes. Or you could imagine pulling a hole from the N-type conductor into the P-type, but again, very similar situation where the N-type semiconductor doesn't have holes. It doesn't have extra positive things to move around. It has extra negative things. So that's why in this reverse bias position, you end up with no current flowing. And if you plot the voltage you apply to this diode against the current, at least for like sort of normal voltages, where not super negative and up to this positive side, you essentially get very, very little negative current flowing. And then if you increase the voltage, you get to a positive voltage, and not necessarily even a very large positive voltage, your current ends up just shooting up with this sort of exponential growth in the current. Right? So that's that forward bias position over here. You increase the voltage a bit, you end up getting a lot of current. In the negative side, or the reverse bias position, you can keep decreasing the voltage and you just get no current essentially. So that's the conventional sort of picture, which is why you call a diode like a one-way valve for current. It just wants to go in the forward position. There is this thing called a breakdown, like eventually if you just keep lowering the voltage, then you're just kind of get to this sort of breakdown position. You do end up getting current going the other way. And there are, in fact, diodes that are designed to do that. I think they're called Zener diodes. That was diodes. Pretty much the simplest thing you could do with these doped semiconductors. The next sort of simplest thing is to kind of sandwich these doped semiconductors. And you end up with what we call junctions, or transistor junctions, or junction transistors, which will either be NPN. In the picture here, you have two chunks of this N-type semiconductor, and they're sort of sandwiching this P-type semiconductor. And they typically have names for each of these pieces. The emitter and the collector are sort of the outside of this sandwich, and the base is the middle. And in a transistor, you have three connections, one to each of those pieces. So one of the very useful things about transistors is they can act as sort of like an amplifier of current. Like the current that flows through the collector is some multiple of the current flowing through the base. And that multiple can be anywhere from 10 to like 100, so that's beta. And a really simple way of seeing that is, like, say for this NPN transistor, if you're able to get a small amount of electrons flowing out of the base, that's a P-type, which means it has extra holes in it, or extra positive charge. And if you're pulling electrons out, you're pulling more negative charge out, you're actually creating more and more holes in that P-type conductor. Now the N-type on either side really wants to start adding some of its electrons to the P-type. So essentially by pulling some of the electrons out of the base, you're sort of highly encouraging electrons to flow through the P-type base. And then the converse sort of picture for the PNP type transistor. So amplification is one very useful thing about transistors, and pretty common usage is what is known as an amplifier, where you take like the current being produced by a microphone. So a microphone has this little diaphragm, that's being pushed in and out by the sound of your voice, or by the pressure produced by the sound waves from your voice. It goes in and out, and there's some kind of electromagnet setup inside the microphone in order to generate a current that's sort of proportional to the pressure and goes along with your voice, the sound of your voice. That current is usually fairly small. In order to actually project that current or do something useful with it, you need to amplify that current. And by using a transistor, that tiny current can be what is controlling the bass, going in and out of the bass. And that adjusts a little bit. Something like 10 to 100 times that current then will start flowing from the collector to the emitter, or the emitter to the collector, depending on how it's set up. But you essentially get 10 to 100 times that current flowing in this sort of top part of the circuit. Another very fundamental usage of transistors has to do with digital signals. You probably know that the information in computers and the way that computers and all this sort of digital technology that we have works is basically ones and zeros. The language of computers is just ones and zeros. You can build up incredibly complicated things by combinations of ones and zeros. And if you think about the transistor, you're actually able to sort of very quickly and easily adjust whether current is flowing through the transistor just by doing a little bit of change to what's going on in the base, right, that middle connection. So by just adjusting the current at the base a little bit, then you essentially turn this transistor on or off. Put a little bit of current in, maybe you turn it on, the current starts flowing through the whole thing. Take that little bit of current away from the base, boom, shuts off. So in that way, transistors can act like gates or switches, and you can switch them on and off very easily by adjusting the current at the base. So you can very easily create signals that are just up or down, right? You get up, down, and there you go. You can just start treating this like up is on, or up is high, or up is 1, and down is 0. And then this digital signal now can be interpreted as digital information. So really quick then, jump all the way back to where we started out with this picture of a integrated circuit. There are like almost 1 billion transistors within this circuit. Crazy to think about. And the way that this has been made possible is by understanding of quantum mechanics, to thinking about atoms, elements, chemical bonds, molecules, solids, crystals, conductors, and so there's semiconductors. Right? All that stuff allows us to get to this place where we can create these incredibly complicated computational things, processors, in very, very small space. Okay, well, the book tries to throw in superconductivity into this chapter too, and my goodness, I guess what to say about that. God bless him. Anyway, this chapter is already very dense. In my opinion, there's a lot of stuff in this chapter. There's a lot of new information. There's a lot of terminology. So we're not really going to say much about superconductors or superconductivity. I think enough to say here, at least, that all of this stuff that we've been discussing basically allows us to get to a point of understanding why some materials will become superconducting at certain temperatures, particularly very low temperatures. And if you haven't heard the term superconductor before, it's a material that has 0 electrical resistance. So current can flow with no resistance, no power loss, no energy loss. It can be a very useful thing. The materials that we know of that become superconducting only do so, like I said, at a very low temperature. And so there's pretty limited places where they're useful currently, and that mostly being in creating like really powerful electromagnets in things like particle colliders. However, there's great amounts of research being done to try to find what are known as high temperature superconducting materials, and if we do get something that would be considered high temperature, there's a vast array of possible applications for superconducting materials. I mean, for one, just power transmission, right? If you could transmit energy without losing power along the way, because we lose a lot of energy in transmission lines. The last thing I'll say is that this high temperature is not necessarily a high temperature that you're thinking of, or might be thinking of, because high temperature in this situation really means greater than the temperature of liquid nitrogen. It turns out that most superconductors that we use now need to be operated in liquid helium. And liquid helium is a temperature of like 4 Kelvin, incredibly cold, but it's also not readily available. Liquid helium is not a very plentiful thing. Liquid nitrogen, however, is very plentiful, easy to get to, or easy to have. And so if we could find a material that is superconducting at above like 77 Kelvin, I think is liquid nitrogen, then that opens the door for a lot more applications, or a lot more practical applications. All right, well, that's it for condensed matter. And next I think we're doing nuclear physics. We'll probably talk about some new forces, a strong force, a weak force. Should be cool stuff. And then the last chapter, we're almost there. The last chapter is the cosmology and particle physics. I hope you enjoyed this, made sense. I will see you in class.